Thank you, Paul. Resource adaptation. So, what are we going to talk about? It's not blank agenda, it's this. Why? Why are we doing this? An overview of ESF TR06 for part 1, which is the specification for it. Some preliminary implementation results, because it's just not talk, we actually done it. And then questions from you. So what's my motivation here? If you use stuff like RIST, you need to, the motivation is you have basic packet loss through retransmission. However, the network capacity may change. So no amount of ARQ is going to fix a situation where you're trying to jam a 5 megabit per second stream on a 4 megabit per second link. So this is something that you must correct at the source. And what you can do is you can reduce the stream bit rate if you know that's happening, or if you have multiple links, you can reroute them or rebalance it. So why do this in RIST? Just telling me to go slower, slower. Why do this in RIST? All right. Source adaptation is a very important feature in some scenarios, and cell bonding is the typical one. In many cases, it's not possible to have reliable transmission with source adaptation. The bit rate is changing too much, and you're going to the lowest is not, basically, you don't have good video. So, if we do this in RIST, we have multiple advantages. RIST already has a framework between the sender and receiver to transmit information. And adding this to RIST has the obvious advantages of multi-vendor interoperability, because you're going to tell me, oh yeah, people have been selling this for years. Yes, but proprietary custom solutions, right? You're locked into a single vendor. So if you do this in RIST, it's an open specification, and then you can achieve interoperability and pick and choose what solution you want. All right. Let me talk about some RIST technical recommendations and show you where it fits. We have TR-06 is RIST simple profile. It's basically low latency, reliable delivery. TR-06 is main profile, which gives you tunneling and security. And TR-06 advanced profile gives you, makes RIST capable of carrying other protocols. So that's a nutshell. And TR-06 are RIST ancillary features. So we have published part 1 and part 2, and this is about part 1, source adaptation. That was approved in November 2022. We also had WireGuard approved January. And there's other stuff we're working on, but that's not the subject of this presentation. All right, here's my framework, right? I have a sender and a receiver, and what we're going to define is this link quality extension messages. So that's what TR-06 part 1 defines, link quality extension messages from the receiver to the sender. Now, you could say, what about this protocol here? Well, if I have a RIST gateway and I can control an encoder, the RIST AG elected not to specify this because it would apply to basically legacy devices. And if you're going to upgrade a legacy device, might as well do the whole thing. So we didn't touch that one. All right. So what is and isn't in the specification? What is? A method for the common method for the receivers to report on link quality. Support for global or per link statistics. So if you have multiple links, you can have individual statistics per link. What isn't? The encoder control protocol, as I said, is not there, and we're not going to do that. And the algorithm to decide how to do the bit rate, that algorithm is also not in the TR-06 part 1. It's not there because it's not necessary. You define a framework to provide the information, and let the vendors innovate. So it's just like MPEG. You can have two encoders both producing compliant streams, and one looks better than the other. So it's open here. Vendors can innovate. All right. That's when I talk about protocols, I'm always afraid that people is gonna fall asleep. So I'm gonna try to go make this interesting. So this is the message. All kinds of bits, all kinds of packets. So it's only 11 parameters in the message. So 44 bytes, you send that periodically. And I gotta tell you about each one of them, but I'm gonna go very fast here, and I just gonna tell me to slow down again. All right, it's after lunch. Okay, we start with a sequence number, so you can identify what the message is, but there is no retransmission mechanism. So consecutive sequence numbers corresponding to consecutive time intervals. So you're reporting over time, and each sequence number says that's the next interval. The reporting period is something else that you use. The TR does not specify how often you send a message. You put it in the message. So what that does that allow is that the receiver can modulate that. If the network's changing too fast, it can send messages faster. If the network's stable, it can send it slow. So the reporting period is not assumed. It's just reported. We throw in the NAC window size just for information purposes. So we have three of the parameters. Next one is count of source packets received. So you see how many packets the receiver has gotten. Count of original packets lost. So there was any that's the incoming packet loss before you did anything about it. Original packets lost. Count of retransmitted packets received. So if you ask for retransmission and they got it, how many retransmission you received? Count of recovered packets. How many packets have you recovered through retransmission? So it's giving you an idea of the link quality. And count of unrecovered packets. That's the bad ones. That's the ones that you couldn't recover with ARQ. Late packets. So this doesn't include original retransmission, just original packets. Late packets are packets, obviously, that came back, arrive at you after the time you needed them. You try to play, it's not there, it's too late. I don't want this packet anymore. There's a late packet. Gives you an idea if your link is well tuned. Measure data bandwidth in kilobits per second. It's important because important to have that. You can derive that from the number of packets, because if you use no packet deletion, the packet size changes from packet to packet. So you have to do that. And measure retransmission bandwidth, same thing, in bits per second. So that's the message. So I described to you 45 bytes of message. Where do we stick it? So how do we transmit that? So there's encapsulations, depends on the profile. Simple profile requires the receiver sends periodically the receiver report, the RTCP receiver report. So there's a mechanism right there. RFC 3550, which is where receiver reports are defined, they includes a mechanism to do a profile-specific extension to the RR. So we simply use that. One of the things that the RIST AG's chairman says is the Lego approach. If there's a piece that you can use, you just use that piece. So we just make a compliant extension of the receiver reports. So this is how it looks like. This is a receiver report. This is an empty receiver report. There was some stuff there already in the receiver report. We took a quick look at it and said, yeah, that's not useful for us. So we need to add more stuff. This wasn't useful. So you either put that or a empty RR. So RC equals to 1 or RC equals to 0. So both work. You just add the information at the end as allowed by RFC 3550. Okay, that was simple profile. What do we do in main profile? That's very easy. Main profile is a tunnel carrying simple profiles, so there's no need to define anything more in main profile. The main profile tunnel simply carries that same information we defined in simple profile. All right, so now what happens on RIST Advanced Profile? RIST Advanced Profile uses RTP but does not use RTCP. We wanted to keep it to a single port, so we can't use the same mechanism. Now, for multi-link operation, I told you it's desirable to have individual per link reports, so you know how each individual link is doing. You cannot do that in simple profile. We didn't design that in simple profile, but here you can do. RIST Advanced Profile has the concept of something called a control message, and that's where we decided to stick this in. We define new link quality report control messages. The payload's the same, but it's a new control message. So this is not a presentation about RIST Advanced Profile, so you gotta trust me, there's a place in there where there's a code and where you can define new messages. So we define new messages here, 2 of them, a global and a link specific. So this is the header of the packet. So think of it as a packet, and then the profile specific extension, it is here. Same message, same 44 bytes, but now encapsulated as a RIST Advanced Profile control message. Multi-link. So let's expand the multi-link, because this is one of the great features of RIST. Multi-link, support for multi-link, with other protocols don't do. Multi-link. So we can now combine multi-link with source adaptation. So we define the global link quality report is the overall, what you're receiving. And we always send that. We send it over all the links, but optionally, you can send specific information about each of the links in that link. So if you're sitting in the link, you're going to have a global message that's the same over all links and gives you the aggregate. And then you can have a second message coming back, which is the statistics specifically for that link. Just remind that simple profile only supports global. So how do we define global? It's a combination of all the information. These packets here include all the duplicates. So if you have multiple links going on, you're going to have a big count. If you have 2 links, it's twice the count if you're using seamless headless switching. The bandwidth, it's also the combined bandwidth over all links. So if you're replicating the stream, you're going to see multiples of the stream. If you're bonding, then it's still the same bandwidth. All right. The link specific are computed only for the packets that are in that link. Not all parameters can be link specific. For example, loss. You don't know which link that the packet's lost on, right? So the receiver has no knowledge. The sender actually has, but the receiver has no knowledge of the packets. So for those parameters, we use global versions. So here's a little table which I copy and pasted from the TR, which shows you which ones are link specific, which ones are global. All right. Encoder rate adaptation algorithm. This is to change the encoder bit rate. This is an informative example. So the TR tells you, you could do it this way, but you don't have to do it this way. The information is there, you do whatever you want. The example is if the number of unrecovered packets is non-zero, in other words, you couldn't recover it, that's bad, you go down. Or if you have packet loss over a certain level. If the number of unrecovered packets is 0, and the number of packets is less than a certain level, the number of recovered packets, the link is okay. Maybe I should go up. So going down is easy, going up is questionable. the implementers can use the information any way they want. So this is just an example. The TR, again, does not specify the algorithm. And now, an example, which credit goes to my friend Adi here, who even did the drawing here for the example. The sender has 3 links. We start with 30% A, 30% B, 40% C. Let's say that link A has an increase in packet loss. You say that link A is going bad. So then I'm going to just do 20, 35, and 45. I just took 10% from here and added it to the other 2 links. That's an example. That's just an example. You can be smart. You can do a better product than your competitor and gain market share by being smart. We allow that in the TR. All right. It's all theoretical, right? Cobalt has not gone and implemented this. So I'm going to show you actual results of the TR implementation. So we implemented part 1, DR6 for part 1, in a RIST-capable encoder-decoder. We just did the simple profile and encoder bitrate adjustment. For this presentation, it's not multi-link. And we fixed the reporting interval to ½ a second. You don't have to do that, but we did that. And the encoder will immediately adjust bitrate if it's appropriate. If it decides that it needs to, you immediately adjust. We also use TR06-2 null packet deletion, and that's something that I kind of glossed over. Many professional-grade decoders need a constant bitrate stream, a constant bitrate transport stream. So how do you do that? Because I'm changing the bitrate. So what you do is you change the video bitrate, you add null packets to compensate. That's what the encoder will do. And then when transmitting, you delete those null packets, but you leave markers so the decoder can put them back. So you get a compliant transport stream, which just more null packets on the other side. But in the link, the bandwidth can be changed. We implemented a variation of the simple algorithm just to see how well it worked. So we start with lab testing. I have just a little test program that can constrain the bit rate, use a simple leaky bucket implementation for the bit rate management, and you can check this box. By the way, this program is, I can give it away if you want, it's a Windows thing. This is on display at the Cobalt booth. This very thing is in there. You have my contact. If you actually want a copy of this program, we give it away. So this is one test. This is time, and this is the encoder bit rate. So what's happening here? I turned the encoder on, so it was off. I turned it on. In here, I enabled the bit rate limit. And then there's uncorrected packet losses because it was abrupt bitrate change. So there's uncorrected packet losses. The encoder goes, ooh, things are bad. Because I'm losing packets, I'm requesting those packets, and those packet requests will cause more packet loss. Things are bad. I go down very fast. And then I start going up. I go up, I go up, I go up. When I get about here, the bandwidth limitation is happening again. So I start to see packet loss. And I say, oops, let me go down. And then I'm going to be doing that. And then what happened here, I turn off the simulator, it goes back one. So in this area here, the encoder basically operated inside the bandwidth envelope that it could operate. And there was no uncorrected packet losses here because it backs down before things get bad. Now, you see that there's a big drop here. Can we do anything about that? Yes, there is a feature in RIST simple profile that can improve things. So here's another test where it doesn't go as much down. So I turn it on, and the encoder doesn't drop as much. Why? Because RIST simple profile is a feature of limiting the retransmission bit rate, throttling the retransmission bit rate. So if you are in a bad situation and you're losing packets, if you try to retransmit those packets as fast as possible, that causes more losses. So this is something that it's simple, but it is in the standard. I'm not allowed to say standard specification. All right, fine. That was in the lab. What about real world? What about the internet, the actual freaking internet? So I have an office here in California, an office here in Champaign, and I'm gonna do that. So what's here? Santa Clara to Champaign. I set my encoder for maximum of 8, minimum of 2.4. I have a 75 millisecond RTT measured by RIST RTT message, because we have that in the RIST simple profile. And I let it run over the weekend, plus a little bit of Monday. Just let it rip. So there's a Comcast cable modem here, not the best thing in the world, and then a fiber provider over here. Okay, so what do we see here? This is the beginning of the test. I turned on the encoder and went to wait. Very quickly found out that, hey, I can't work there. Went down and see, it could get to wait for a few minutes here. So this is the first 45 minutes of operation. And this is the whole 64 hours. I have no idea what happened here, but it went to the bottom. But it was able to go up to the top for a lot. If any of you went to VTrans, yeah, he went to VTrans. I had this running at VTrans over the internet at VTrans. In fact, I had it running for a little bit in my hotel room over the freaking hotel Wi-Fi and was still working. It didn't go to 8, but it was, I got 0 packet loss and a valid SDI signal out of this. All right, lessons learned. We're slow, but we learn, right? I learned. The best results are obtained if the sender is aggressive in reducing the rate and slow to increase it, right? We can operate that way in a capped bit rate environment. There's other improvements you can do, but then I'm gonna go tweak my product and make it better. You go tweak your product and make your product better too. The other thing we obviously, if you're sending one-to-many, so multiple unicast or multicast, you need to keep state on a per SSRC basis, SSRC of the receiver. So this guy's reporting that, and you make decisions based on the worst case feedback. I did disagree, so we'll have a discussion after this. If the sender is using seamless switching, the protocol itself will combine the results. And that's that. Any questions? Yeah, go ahead.
What do you need from the encoder so that it will do the changes? Will it start and stop, or it's continuous?
I mean, if you want a seamless change, it needs to be continuous. Proper encoding engines can receive commands to change bitrate dynamically. I'm getting my butt kicked here. Well, the Cobalt encoder will do that. The Cobalt encoder will do that. It's helping you with marketing.
There are many tier 1 encoders that can basically be controlled. I won't name names, but mostly tier 1, even tier 2, some even tier 3 that can do that. But things like FFmpeg type of solutions will not do that. There is a different approach need to be taken there.
Yes, if you're doing rate adaptation on the encoder, because you cannot do source adaptation over paths, right? Your encoder needs to be able to, on the fly, change the bit rate without stop and start. Otherwise, what's the point? You're going to glitch. Any other questions? All right, thank you.